This is the first lecture of Chapter 17, which deals with aldehydes and ketones. As we have seen from earlier chapters, they are very important molecules in organic chemistry. So, in this lecture, we will be looking at the following, or discussing the following. First, we'll re-examine the aldehyde and ketone functional group. So we'll look at those again and make sure you can identify those functional groups in organic molecules. And next we'll look at some common compounds in nature that are aldehydes and ketones. As I mentioned earlier, they are very common in natural products. We'll next look at the nomenclature of aldehydes. As I mentioned in previous lecture, the nomenclature is very important in organic chemistry. Why? Because that is how we communicate to other chemists and scientists. So if you discovered a new compound, you have to give it a name. And in order to communicate that name per structure, you'll have to use a systematic way that everybody understands. And that's the IUPAC nomenclature. Then we look at the nomenclature of ketones. Lastly, we look at the properties of aldehydes and ketones. Of course, as you will recall, properties are basically measurable or observable characteristics of compounds. They tend to be unique for a particular molecule. Lastly, we look at the applications of these properties to some of the everyday molecules that we'll discuss. Okay, let's begin. So, the first thing that we need to be able to identify is the aldehyde and the ketone. In order to do that, there's one aspect that's common to both, and that is the carbon-oxygen double bond. And here it is, a carbon and an oxygen double bond right here. They are present in both aldehydes and in ketones. The difference, however, is what is bonded to the carbonyl carbon here. So here's one possible bonding, and here's another possible bonding. So because there are 4 bonds to carbon, here 2, it can bond to 2 other groups here, and what's bonded to these to this carbon will in fact determine the aldehyde and the ketone. For example, if both were hydrogens bonded right here and here, so here's the carbonyl or the carbon-oxygen double bond. This is a specific molecule and it's known as formaldehyde. That's the main ingredient in preserving most of the biological organs that we see in the biology lab. Here's another type compound, an aldehyde. Here's a carbonyl again, carbon-oxygen double bond. It has a hydrogen. If this is bonded to a carbon-containing alkyl group that we mentioned here as R, it's an aldehyde. Key is one group is a hydrogen and the other group is a carbon containing alkyl group. I'm emphasizing carbon. Here's the other one. Here's a carbonyl or the carbon-oxygen double bond. If it's bonded to 1 and 2 carbon containing alkyl groups, Then we have a ketone. Why am I emphasizing carbon containing? As you've seen, if this were an oxygen, that would be a totally different functional group. Could be an ester or a carboxylic acid. So if it's bonded directly to a carbon containing group, it could be an aldehyde or ketone depending on if a hydrogen is present also. So as a summary, an aldehyde has the carbon-oxygen double bond. It has one carbon-containing alkyl group and one hydrogen. The ketone has the carbonyl or the carbon-oxygen double bond. It has one and two alkyl or carbon-containing alkyl groups bonded to that carbon of the carbonyl. So here's another summary, another way of looking at it, or another summary here. So an aldehyde is bonded to a hydrogen and a carbon-containing group. And of course, formaldehyde is a specific example because it has just two hydrogens. A ketone has two carbon-containing groups. Keyword: two carbon-containing groups. Here's some examples. This is the carbonyl right here, and this carbon of the carbonyl is bonded to a hydrogen and a hydrogen. That makes it a specific molecule known as formaldehyde. Here's another example. Here's a carbonyl. It's bonded to a hydrogen and a methyl group back here, carbon containing. Therefore, this is an aldehyde. Here's another example. Here's a carbonyl. It's bonded to a methyl carbon group and another methyl carbon group. That makes it a ketone. This is a very specific one here known as acetone. That's a very common organic solvent. Let us look at some that are found in nature, aldehydes and ketones. Here is one, vanillin. The organic molecule is here. First, is it an aldehyde or a ketone? We'll have to identify the carbon-oxygen double bond. Here it is. This carbon is bonded to one hydrogen and another carbon with that group. So therefore this is an aldehyde. So vanillin is an aldehyde, which is the vanilla flavor that's used in baking, etc. Here's another natural product, carbone, main ingredient in spearmint flavor. Here's a carbonyl, or the carbon-oxygen double bond. It's bonded to a carbon and another carbon. So therefore this is a ketone. Here's another one, cinnamaldehyde. It has a carbon-oxygen double bond, or the carbonyl group. It's bonded to a hydrogen and another carbon-containing group. Even though that's a double bond, but it's still a carbon-containing group. So therefore this is an aldehyde, which is known for the main ingredient in cinnamon, or the cinnamon flavor. Benzaldehyde is another ingredient, natural product found in almond flavors. And is it an aldehyde or a ketone? Here's a carbonyl. You can tell. You'll have to identify or be able to identify the carbon-oxygen double bond. This one is bonded to a hydrogen and a carbon-containing group. So therefore this is another aldehyde. So you should be able to look at an organic molecule, no matter how complex it looks, but you should be able to determine if it has an aldehyde or a ketone functionality. Let's look at the nomenclature. As I mentioned, the IUPAC, International Union of Pure and Applied Chemists, deduced rules so that we can effectively communicate the names and structures of organic molecules. So first, let's look at the nomenclature of aldehydes. So first, you'd have to identify the molecule as an aldehyde or not. Let's look at this molecule here. It is an aldehyde because here's a carbon-oxygen double bond. It's bonded to a hydrogen and a carbon alkyl group. So therefore it's an aldehyde. First rule is you'll have to number, starting with the carbonyl carbon as 1. So this is 1, 2, 3, 4, and 5. Notice we do not start at the other end. So this is wrong. This is the incorrect numbering system. Start here at number 1. And of course, why do we do that? Because we'll see over here that if it has 6 carbons, for example, here is 6 carbons here. So that becomes a hexane because 6 corresponds to hexane. You may recall that you memorized that way back when we started the course. So what we do is we change the E of the alkane or hexane to Al. So it becomes an alkanal. So this molecule here has 6 carbons, and as we said on the previous slide, we start numbering here. So 1, 2, 3, 4, 5, and 6. Hexane, it goes from E to Al, so it's an hexanal. You could put here 1 hexanal to indicate that the aldehyde functionality is in position number 1. But it will always be in position number 1, so that's understood. Here's another example. 1, 2, 3, 4, and 5. 5 carbons. Pentane, so it goes to pentanal. Notice this Al here indicates the aldehyde. And of course we could put the 1 here again to indicate that 1, but it's not needed. But the main thing here is the pentane to represent 5 carbons in that longest chain that has the carbonyl aldehyde. Let us look at branched aldehydes. So if there's a branch on that chain, how do we name it? Same systematic approach applies. We identify first of all the functional group as an aldehyde, and why? Here's the H, here's the carbonyl, and here's the carbon that's bonded to it. So it's an aldehyde. How many carbons in the longest chain? 1, 2, 3, 4, and 5. So it becomes a pentanal, Al. And of course, if we have it numbered, we just need to put the groups that are bonded to this longest chain here. So here's a methyl group. Here's another methyl group. And it's on carbons number 3 and carbon number 4. So we have 3, 4 dimethyl. Don't forget that di because it's 2 methyls. Here's another example. Here's the aldehyde. So we give it number 1. So 1, 2, 3, 4, 5 this time. So it's a pentanal. And we have a branch here, which is an ethyl. And we have a branch here, which is a methyl. So, as we know, E comes before M. So it's a 2-ethyl, Y2, because it's on carbon number 2. And a 3-methyl, Y3, because this methyl group here is on carbon number 3. So the name is 2-ethyl, 3-methyl pentanal. Sounds like a complex name, but as you see, it's just a combination of different portions of the molecule. So let us see if we can apply that rule here. So give the line angle structures for the following molecule. So this question is designed to make sure you fully understand the concept of naming aldehydes. So you need to go from structure to name, and also from name to structure, because that's really creating and generating that thinking and the application of that knowledge to solving problems. So here is a name of a compound. First of all, we need to recognize what is the functional group present. The functional group present is always at the end, Al. So that's an aldehyde. It has 5 carbons because it's a pentanal. So you may want to do and put your aldehyde at the end here, and even number it just to make sure you don't miss anything here. So here's 5. Now once you have it numbered, you just have to look at the groups and where they're placed. So here is a 3-chloro. So on carbon number 3 is a chloro. 4-methyl on carbon number 4 right here is a methyl group. The answer is on the next slide, so we'll look at that. Here's another example. What is the functional group present in this molecule? Here it is, Al, aldehyde. So again, we have 5 carbons. Don't forget that H. So we have 1, 2, 3, 4, and 5 carbons for pentane. And then on carbon number 2 is a chlorine, so put a chlorine right here. And in carbon number 3 is an ethyl, so put an ethyl, 2 carbons right here. So let's look at the answer. So here we have 1, 2, 3, 4, 5 carbons for the pentanal, and the Al is right here. And of course on carbon number 4 is a methyl group, and in carbon number 3 is a chloro group. So again, you should be able to go back and forth between name and structure. Here's the other one. It's a pentanal, Al, here's the aldehyde right here, and 5 carbons, pen means 5, and of course on carbon number 3 is an ethyl. Notice this is an ethyl because it has 2 carbons, 1 carbon, 2 carbons, and on carbon number 2 is a chloro, and here is the chlorine. So once again, you should be able to go forwards and backwards between name and structure. Let us look at how we name an unsaturated aldehyde. Unsaturated. Unsaturation here means that you have a carbon double bond. I'll put 4 lines here just to make sure that we have 4 bonds to a carbon. But the main thing is we have a carbon-carbon double bond for the unsaturation. So in these molecules, you'll have 2 main functional groups. One is an aldehyde, and the other is a double bond. So let's look at this example here. This molecule has an aldehyde right here, and it has a double bond right here. How do we name that? We start from the aldehyde. That takes priority over the double bond. So this is 1, 2, 3, 4, and 5. So it becomes a pentanal. We change the E of the pentane to Al. We know that. And that is for this carbon aldehyde right here. We have to indicate the presence of the double bond. That's indicated by this E right here. So we change the A from the alkane to E, so it's an alkenal. So this becomes a pentenal. Make sure you write an E and not an A, because once you write an E, it is indicating the presence of unsaturation in the molecule. You'll have to indicate where that double bond is, or the carbon-carbon double bond. It's on carbon number 3. Here it is. Why number 3 and not number 4? Because we're numbering in this direction. So wherever that double bond starts, whatever carbon that falls on, that is the number we put right here. And of course there is a methyl group on carbon number 4, so it's a 4-methyl. So let's go over this just to make sure we have it. This is a molecule that has an aldehyde and a carbon-carbon double bond, or an unsaturation. So we'll have to first of all determine the number of carbons in that chain. 5 carbons. So the root would be pentane. Since it's an aldehyde, it goes to pentanal. Since it's unsaturation, there's an E to represent the alkene. And we'd have to indicate the location of the alkene with a number from that chain. And of course, if they're substituents, we give that substituent a number and a name as shown here. So let's apply that over here. So here are some examples. So here is a molecule that has an aldehyde. We know it's an aldehyde because of that H. It also has a double bond, an alkene, so it's an unsaturated aldehyde. How do we name it? Aldehyde gets priority in terms of numbering, so we start 1, 2, and 3. 3 carbons represents a propane, so we have a propanal to represent the aldehyde. And of course there's an E here to represent the alkene. And we'll have to indicate the location of the alkene with that number. Again, why 2 and not 3? Because we're numbering in that direction from the aldehyde. Same here. We have a double bond right here, and it's an aldehyde also. So it has 1, 2, 3, 4 carbons, so it's a butanal. And of course there's a double bond, so this gets an E to show that there's an unsaturation present. Where's that double bond? It's on carbon number 2, which is indicated right here. And of course there's a methyl group right here. And of course it's on carbon number 3. And here's that 3 to represent that methyl. Last example. Here's an aldehyde and an alkene. So as you can tell, whenever you get these problems, you'll have to first of all carry out your observations. You have to look at that molecule carefully to determine the functional groups present and which one will be used as the main name. It's an aldehyde, so we start with 1 here and go through to 6, so it becomes an hexanal. This Al represents an aldehyde. There's a double bond starting at carbon number 3, so here's that 3, and here's that E to represent that double bond. Here's an ethyl group. So we have, and it's on carbon number 3, so it's 3-ethyl. Here's a methyl group, and it's on carbon number 5, and here's that 5 for the methyl. Notice again that we have a hyphen that's used to separate letters from numbers, or numbers from letters. Please include those. As a summary, so if you have an aldehyde, so look at your molecule carefully. If you identify it to be an aldehyde, the E from the parent goes to Al, so it becomes an alkanal, so it's pentanal, hexanal, butanal, etc. The numbering, the carbonyl carbon always gets number 1. If there is an unsaturation or a carbon-carbon double bond present, it goes from EA to E, so it becomes an enal, an alkenal, an hexenal, or propenal, etc. Make sure you write the E carefully. Take your time to write that E so that the graders can see that it's an E and not an A, because an E represents a carbon-carbon double bond, and A would represent a saturation or no double bonds present. Let us turn our attention now to ketones. How do we name ketones? First, you'll have to recognize the molecule as being a ketone. How do we do that? We have to recognize, as I mentioned earlier, the carbon-oxygen double bond. Since here's the carbon, that's the carbon of the carbon-oxygen double bond, it's bonded to a methyl group here, carbon-containing, and another carbon-containing group here. This is a ketone. So, we're just looking at numbering. So once you have identified a ketone, start numbering closest to the ketone functionality or the carbon-oxygen double bond. So start here and not over here. So this is not correct, but start here. Notice this does not get 1 anymore because it's internal. It's in the chain. It's not at the end as the aldehyde. So this gets number 1, 2, 3, 4, 5, 6. So that's just how you number it. How you actually name it is shown here. So if there's 6 carbons, the E from the alkane or the hexane goes to one. So it goes from alkane to alkanone. Notice the E goes to ONE. So once you see an ONE, you know you have a ketone. So here we go. Here's the same molecule we had before. We know we start numbering here because that's 1, because it's closest to the carbonyl of the ketone. So it's 1, 2, 3, 4, 5, 6 carbons. We know 6 carbons correspond to hexane, so it goes to hexanone. ONE, to indicate that it's a ketone. Since the carbonyl of the ketone can be on any of these carbons because it's internal, we'll have to indicate the location of this. For this molecule, it's on carbon number 2, so we put a 2 here to indicate the position of this one. Here's another example. Here is 6 carbons again, so that's hexanone. How do we know it's an one? Because here is the ketone. We start numbering at the end closest to the carbonyl or the carbon-oxygen double bond. And so we'd start here, 1, 2, 3, 4, 5, 6. This carbon-oxygen is now on carbon number 3, so it's 3 hexanone. Notice you have to put the 3 in because, as you can see, it could be on any of these internal carbons. Don't forget the hyphen between the number and the letter. So let us look at some examples here. So we'll just quickly go through these. So here is an example. So we have the ketone here. We know it's a ketone because here's a carbon and here's a carbon. So it has to be an one. How many carbons? 5. So it's a pentanone. We start numbering here. This carbonyl or the carbon-oxygen double bond is on carbon number 2. So we'll have to indicate that 2 to show that this is for the one. And here's a methyl group on carbon number 4. Let's look at this one. 1, 2, 3, 4 carbons again. It's a ketone, so it's a one. 4 carbons, butanone. The carbonyl here is on carbon number 2, and here it is. And we have 2 methyl groups, so this would be a dimethyl. for 2 methyl groups, and it's on carbon number 3. So we'll have to indicate that by 3,3 dimethyl. Again, notice this is a comma. A comma is used to separate two numbers. Another example we'll go through quickly here is, recognize this to be a ketone. So it's an one. 1, 2, 3, 4, 5 carbons. So it's a pentanone. And the carbonyl is on carbon number 3. And here's a methyl on carbon number 2. So here is that 2. And last example here is, recognize this again as a ketone. So it's a ketone. If you recognize it as a ketone, it has to be an one. So it's how many carbons? 5 carbons. So it's a pentanone. We have to indicate the position of this one. It's on carbon number 2. So here's that number 2. And of course, here's a methyl group on number 3. So that's how we name it. Let us look here at a little more complex molecule. This one here is an unsaturated ketone. So what we'll find here is a carbon-carbon double bond and also a ketone. So, as you can imagine, the ketone takes priority over the carbon-carbon double bond, but we'll have to indicate the position of the ketone and the position of the carbon-carbon double bond. But first, you'll have to recognize the molecule to be a ketone. So let us look at this example. Here is the molecule here. Is it a ketone? Yes, it is, because here is the carbon-oxygen double bond. This carbon here is bonded to another carbon and to another carbon, even though it's a carbon of a double bond, but it's still a carbon. So therefore, this is a ketone. If it's a ketone, it has to be an one. As we mentioned, because the one can be anywhere in the molecule, it's an internal functional group, we have to indicate the position of the double bond, the carbon-oxygen double bond this time. So we use a number, 2. In this case, it's on carbon number 2, so it's a 2-one. Notice we have to break the name up. We have to split the name because it becomes very complex if we write it all in one word. But here's the E. This E here is to represent this carbon-carbon double bond. Make sure you put that E in and not an A, because that E represents the double bond. What's the location of that double bond? It's on carbon number 3. Why carbon number 3? Because we're numbering in this direction, and the carbon of the double bond which first appears gets that number. So 3. So this 3 here is to indicate the position of the double bond. And of course, on carbon number 4 is a methyl group, so here's 4-methyl. Quite a lot. So let's review this, and then we look at some examples on the next slide. So once again, if you have a difunctional molecule where it's unsaturated, where you have a carbon-carbon double bond, unsaturated, and also a ketone carbon-oxygen double bond, how do you name it? The main aspect here is the one is to indicate the position of the ketone, and the E here is to indicate the presence of a double bond, carbon-carbon double bond, but we'll have to indicate the location of the one, and we'll have to indicate the location of the ene, as shown here. Let's look at some examples. So here's an example. So this molecule here, you have to recognize it as a ketone. Here's the carbon-oxygen double bond. we start numbering at the end closest to the carbon-oxygen double bond. So it's 1, 2, 3, 4, and 5. 5 represents a pentane. So, but since it's a ketone, it's an one, and it's on the one is on carbon number 2, which would have indicate here. It's a pentene because of 5 carbons. It's an ene because of this double bond right here. It's on carbon number 3, so we have to indicate that with a 3. And of course there's a 4-methyl right here. So it's a 4-methyl. So again, looks very complex, but it's just a systematic way of putting all the pieces together. 4-methyl, 3-pentene, 2-one. Here's another example. It's a ketone. The carbon oxygen is on carbon number 2. There are 4 carbons in that longest chain, so it becomes a 2-one. Notice this one here is to represent the ketone. And of course here is a double bond on carbon number 3, and here is the E to represent that double bond. So it's on position number 3, location number 3 right here. Also on carbon number 3 is a methyl group. And so it becomes a 3-methyl 2-butene 2-one. Make sure you write this E legibly so the graders can see it's an E and not an A. Here's another example. So here we have, recognize this to be a ketone again. Here it is. Start numbering at the end closest to the double bond, closest to the carbon-oxygen double bond. Let me emphasize that. Start numbering at the end closest to the carbon-oxygen double bond because we're naming it as a ketone. So there are 5 carbons, and the location of the carbon-oxygen double bond is in position number 3, so it becomes a 3-one. Again, this is for the ketone. It has a double bond. It's in position number 1 because we're numbering based on the ketone, so it's 1-pentene for the E double bond. And of course on carbon number 2 is a methyl group, and here's the methyl group, and here's a 2 to indicate the position of that methyl group. Last example. Here's another molecule. So identify the one. Here it is. Start numbering closest to that one. So it's 5 carbons, but the one is on carbon number 2, so it's a 2-one. 5 carbons, pentene, but then again there's a double bond on carbon number 4. So it's 4-pentene, 2-one. And of course there's a methyl group right here on carbon number 3. So it's a 3-methyl 4-pentene 2-one. Sounds complicated, but once you put together the pieces, it's not really that complex. Okay, so let's look here at cyclic ketones. Cyclic ketones. So as you can imagine, the ketones can be in a ring. Notice the aldehydes cannot be in a ring because it's at the end. But the ketones, because it's internal, it can be in a ring. So again, to name it, identify the carbonyl. Here it is, or the carbon-oxygen double bond right here. It gets number 1. And you continue numbering in the direction of the branch. So here's a branch. 2 chloral groups. So we number in this direction and not this direction. So we go in this direction of the branch. So once you have that appropriately numbered, you can see this is a 3-3 dichloro. Since it's a cyclic system with 6 carbons, it's a cyclohexane and of course one, cyclohexanone. We need not put one on. Let me just write what we need not put. But if you put it, it's not wrong. You could have put 1,3,3-dichlorocyclohexane 1 on, but because it's number 1, it's understood. So you need not put that in. Let's look here at the double bond or the unsaturation that's present in ketones. Same systematic approach. The key here though is to change the E to cycloalkenone. Change the A, change the A of the cycloalkenone to an E. So it becomes a cycloalkenone. Don't forget the cyclo because it's a ring. So let's see how we can apply that. So here's an example. Recognize this to be the carbonyl or the carbon-oxygen double bond. And this carbon gets number 1 because we're naming it as a ketone. So it has to have the priority. So it gets number 1. In this case though, we number in the direction of the double bond. So we go in the direction of the double bond, not in the direction of the branch. So if there is an unsaturation, we go in the direction of the double bond. Remember, unsaturation here means a carbon-carbon double bond. So the numbering goes here. Once you have the numbering, it's just a matter of giving the name. So here we go. Correct numbering is this and not here. So this is incorrect because we're going away from the double bond. Here's the double bond right here. We have to go in the direction of the double bond and not away from it. So this becomes a 5-chloro. Here's the 5 and the chloro. And here we have 2-hexene. Here's the E for the double bond. It's on carbon number 2, and here's that 2. So again, systematic way. That's why it's called the systematic nomenclature of organic molecules. It's just a matter of using a systematic way so that chemists from around the world can understand and communicate the names and structures of organic molecules. So once again, that's how you actually name unsaturated cyclic ketones. Okay, let us turn our attention now to the properties of aldehydes and ketones. So here's an aldehyde, or a carbonyl. This one is a specific one because it has H and H, so it's formaldehyde. But the main thing here is that it has a carbon-oxygen double bond. So this is a polar covalent bond. Why polar? 2 poles. Oxygen being more electronegative. Look at your periodic table. You can see that oxygen is to the right of carbon. So therefore these electrons here are much closer to the oxygen than they are to the carbon. So that creates a pole, a dipole, or a polar molecule, where this is partially negative because of the electrons being pulled closer to oxygen, and this is partially positive because the electrons are pulled away. Remember, electrons are negative from carbon. So it is a polar molecule. So aldehydes and ketones are polar molecules. So what's the consequence of the polarity of aldehydes and ketones? They are soluble in water. Soluble in water. So here's water. And of course, as you know, water is a polar molecule. What is a polar molecule? where hydrogen is bonded to oxygen. Oxygen is again a very electronegative atom. So these electrons over here, and this is partially negative and partially positive. Very polar molecule. Because this is partially negative from the aldehyde or ketone, there's a potential for an attraction. This type of attraction is called a hydrogen bond because of the hydrogen from water. So notice again, these molecules here, they do not contain a hydrogen bonded to an oxygen. It's the water that contains the hydrogen, so therefore the hydrogen bonding is present because of water. So that's why aldehydes and ketones tend to be soluble in water. I say tend to be because it depends on the R group back here. If it's pretty large, it's not as soluble, but if it's pretty small, such as CH3 here and a CH3 here, which would make it acetone, of course, as we know, acetone is very soluble in water. Let us look at another consequence of the polarity. So here is a representation of a ketone in this case, because we have two R's. But the bottom line is this bond again is demonstrated to be polar. Partially negative, oxygen, because oxygen is a lot more electronegative than carbon. So we designate that by partial negative. There's a Greek letter here that's used to represent partial negative. So it's a polar molecule. So since this is partial positive and partial negative, in the presence of another molecule with a partial positive and partial negative, if it's oriented in this way, we have an attraction. Because of course, as you know, a partial negative will be attracted to a partial positive. Opposites attract. This is not a hydrogen bond because there are no hydrogen involved here. So it's called a dipole-dipole attraction or dipole-dipole interaction. So they're weak interaction, or should I say they're much weaker interaction than your hydrogen bond. But there is an intermolecular attraction here that's not hydrogen bonding. Notice no hydrogen bonding because there's no hydrogen, but they're called dipole-dipole attraction as shown here. Let's look at the consequence. So as you can see here, so let's concentrate on just a couple molecules here. Here is butanal and butanone and butanol. Notice the names are pretty similar. Here's OL and here's AL, but we know the AL represents an aldehyde. Look at the molecular weight, pretty much the same. Look at the boiling point, 76, but look at the boiling point for butanal, 117, much higher. Why? Because butanol, an alcohol, can be involved in hydrogen bonding. Butanal, which does not have a hydrogen bonded to an electronegative oxygen or nitrogen, or in this case oxygen to be specific, there are no hydrogen bonding, just dipole-dipole attraction. So therefore that's why the boiling point here is lower. Let's look at butanone, 2-butanone. It's a ketone because of the ONE right here. The boiling point, the molecular weights here are just about the same. Well, it actually is the same, but you can see the boiling points here are pretty similar and much lower than that of the alcohol. Why? Because there are no hydrogen bonding that's possible between molecules of butanone, and there are no hydrogen bonding between molecules of butanal, but there are hydrogen bonding between molecules of butanol because it's an alcohol. So just a summary here before we conclude. So for liquids of aldehydes and ketones, they're weak, notice weak intermolecular attractions based on the polar covalent bonds. Again, there are no OH or NH present, so therefore they cannot participate in intermolecular hydrogen bonding. They can participate in a hydrogen bonding with a solvent, such as water, but not between themselves. So aldehydes and ketones tend to have lower boiling points than alcohols, and we'll see later on carboxylic acids. But the main thing here is for alcohols, because alcohols have the possibility of hydrogen bonding, and ketones and aldehydes do not have the possibility of intermolecular hydrogen bonding. I think that's the end. That's the end. So once again, this is the start of a new chapter, primarily dealing with the nomenclature and the properties of aldehydes and ketones. The next lecture we'll look at reactions. So make sure you understand the naming of these molecules. Make sure you can identify these functional groups in different molecules, because the next lecture will be on the reactions. So you'll have to be able to identify these functional groups so that you can predict the reactions with different type reagents. So continue to study hard, and remember again that we're not just here to learn the facts of organic chemistry. That's good, but we're also here to apply these facts and knowledge to solving different problems. Okay? Continue to study hard.